organizers to give a sort of colloquium level introduction. So that's my plan. I look around the room, I see many of the world's leading experts on the subject, so many of you, you can go get coffee or something for now. But hopefully it will still be of interest. I'm going to cover 3 topics. What is eigenstate thermalization? What follows from it? What good is it? When does it hold? And then I will talk about some recent developments that I think are interesting and should be of interest even to the experts. So. All right, so what is eigenstate thermalization? This has now come into the phrase eigenstate thermalization hypothesis. So we say that, first of all, we want to think about an isolated many-body quantum system. So no external forces, many-body, n has to be large enough that we can contemplate doing statistical mechanics, and everything will be quantum. And so we say that such a system obeys the eigenstate thermalization hypothesis if the energy eigenstates of this system look like states of thermal equilibrium in the following sense. So I'm going to define what I'm going to call a local observable. What local means depends on the system. In a lattice system, I mean something localized in a region. In something like a gas, I mean something that depends only on a few of the degrees of freedom, so a few body observable. I is an energy eigenstate at some energy E, and I didn't put it on the slide, but this should be at a high enough energy that we can think of the energy density as a finite number. We don't want to be close to the ground state. In terms of temperature, we want to be at a finite temperature and not taking any sort of zero temperature limit. All right, and then the statement is that the expectation value of such a local observable in a sufficiently high energy eigenstate is equal to a thermal expectation value plus 1 over n discrepancies. And for thermal here, you can take whatever your favorite thermal average is. You can take a microcanonical average in some slice around this energy, or you can take a canonical average at a temperature that corresponds to that energy thermodynamically. And here we already see the reason we need large n. Those different ensembles will give answers that differ by terms of order 1 over n. So we want to be in a regime where n is large enough that the different ensembles give the same answer to the tolerance that we care about. Okay, and this piece of it is sometimes called diagonal ETH. There's another piece that we also need. We need the off-diagonal matrix elements, meaning I put 2 different energy eigenstates on each side of A. We need those off-diagonal matrix elements to be small in some suitable sense that I will get to. Okay, and so there are numerous antecedents of this in the literature, but Josh Deutsch in 91 and me in 94 wrote papers that codified this more generally. And so this is sort of, and I think I coined the phrase eigenstate thermalization.
One question.
Yes.
N is the number of, it seems to be the number of particles, but can also be the dimension of the Hilbert space.
It is not the dimension of the Hilbert space. N is the number of particles or number of degrees of freedom, within some order 1 factor. But the dimension of Hilbert space will generically be exponential in that n. Any other questions at this Okay, so those two statements can be codified into what is now often called the ETH ansatz for matrix elements in the energy eigenstate basis of one of these local observables, which takes the following form. First of all, there's generically a diagonal term with some function script A of the energy, where energy is now defined as the average energy of the two eigenstate energies. And then there's well, this can also include a diagonal term, but there are off-diagonal terms. And the most important thing here is this factor of e to the minus s over 2. E to the s is the density of quantum states, and so this is what you should think of as the dimension of Hilbert space. And as usually happens in a many-body system, this thermodynamic entropy scales like the number of degrees of freedom. We're also going to want to think of this average energy as scaling like the number of degrees of freedom. That corresponds to what I said previously about finite energy density. But the energy difference, it will be useful to think of that as scaling like a number of order 1. And then what we have here, we have this is the small factor that we needed. Then there's some basically fudge factor that's a function of those two variables. And then there's some, quote, random, unquote, number. I like to use the word erratic, so it varies erratically. But if you average it over some range of energies in I and J, where the range is small on the scale on which these functions are varying, but still covers many states, that average should have a zero mean and a unit variance. And the differences in variance are encoded in this F function. Okay. All right. So this matrix element ansatz essentially is what is meant by the eigenstate thermalization hypothesis, that the matrix elements of local observables take this form. Oh, and I didn't say it, I wrote it. These are smooth functions. They don't jump around erratically with I and J. That's what this R is supposed to do. But in particular, this diagonal term is a smooth function of the energy and is not jumping around as the energies vary. Okay. Why would we care about such a thing? Why does it matter? So the main thing that follows from this is a conventional stat mech for pure states in the following sense. So I'm going to assume I have my state of the system is a pure quantum state, which I get by superposing energy eigenstates with suitable coefficients, and then the Hamiltonian time evolution we throw in these phases. I've set h bar to 1 because I started life as a high energy theorist, and we always set h bar to 1. It's not written here anywhere, but it's necessary that when we create this superposition, we're superposing energies that are in a window of energies that's sufficiently small that we don't have to worry about the quantum uncertainty in the energy. So, for example, if we were to use a thermal density matrix, the energy scales like n, and the quantum uncertainty in the energy scales like the square root of n. So I want some sort of scaling like that, so that the states which are being superposed here, the dominant ones all have nearly the same energy within some window that we can think of as macroscopically small in terms of measurements we might make. Okay, now I want to follow or construct the expectation value in this time-dependent quantum state of one of my local observables, and just plugging in the formula, and we get this result. And what we would like this formula to do I claim, is agree with the following picture. So first of all, I want to start out my state in a state that's does not look anything like a state of thermal equilibrium. So I want the initial expectation value of A to be far from its thermal value, because that's the interesting thing to look at. But then what we expect to happen is that this expectation value will move to the thermal value and then stay there most of the time, but with possibly fluctuations. So this curve is an artist's conception of what should happen. Fluctuations are actually quite exaggerated, but that's what we expect to happen. And the claim of ETH is that this formula will reproduce this picture for the following reason. First of all, these diagonal elements, AII, those are given by that smooth function script A of E. And again, as I just said, we want to sum states over a window that's macroscopically small. That means small on the scale on which these matrix elements are varying. And since that window is small on the scale on which the matrix elements are varying, the matrix elements are essentially a constant. I can take them outside the sum, and then I just get 1. So no matter what these C's are, as long as the energy window they're covering is not too large, we'll get the same answer. And according to statistical mechanics, that answer should be the thermal average. So we can conclude that that smooth function, what it's actually doing is computing the thermal average for us. And this term will then, this time-independent term will then be the thermal average. These terms are, every term in here is really small because each of these off-diagonal terms has an e to the minus s over 2 in it. So most of the time, each of these terms and their sum is going to be very small, but by cleverly choosing C's, we can get this term to be big. We know that's possible because we know we can construct states that are not states of thermal equilibrium. So we've chosen C's that do that at time 0, but even if they do that at time 0, once the phases start turning on as time goes forward, the coherence that we needed for these many, many very small objects to add up to one big object that competes with the thermal average, that phase coherence is destroyed, and we expect this to go down to 0. That's the basic idea. This is what the ETH matrix element structure does for us. It tells us that the time-dependent expectation values of observables will behave the way we would think they behave because we all took that class in statistical mechanics. Question?
No chance for revival?
Oh, there will be a revival, but it will be very much later, typically. Right? So it will take it will come at the Heisenberg time, which is 1 over the level spacing. The level spacing is e to the minus s, so it comes at e to the plus s generically. Now, of course, it might happen sooner. And you know, I could do some more formal manipulations of this to show that the time average, the fluctuations over time are very small. The time average of the fluctuation. So there can be recurrences, but they can't last for very long.
If I have a system that does equilibrate but not thermalize, what changes?
Well, you have to tell me what the difference between equilibration and thermalization.
Well, mostly that the value you're converging to will not be a thermal one. Will not be given by a Gibbs ensemble in that sense.
Will it be given by a generalized Gibbs ensemble?
Maybe, or maybe not even that. So
Okay, well, such a thing would not fit in this framework.
I'm just wondering whether a very similar framework wouldn't apply as well, but...
Well, the similar framework that I would say applies is a generalized Gibbs ensemble invented by Marcos and friends. that says you should put in a temperature-like parameter for every conserved quantity.
Yeah, and or like a many-body localized system, assuming
many-body localized,
assuming that it exists.
Yeah, no, that's a phenomenon where the system sort of generates its own approximate conservation laws, and again, that would not fit into this framework.
So can you clarify that generalized Gibbs ensemble? That
later.
Oh, later. Okay.
I'll clarify it later.
Okay.
Is this somehow the same as a diagonal ensemble? Or?
Well, diagonal, yes. So this term is the diagonal ensemble, where we weight the energy eigenstate expectation values by the c-squareds from some initial state. And again, the statement is that it doesn't matter what those c's are because basically the AIIs are all the same.
If you order the energy in some increasing order, can you put some metric on the Rij that you define? So can you kind of find the notion that they decay if the two energy levels are far enough?
So I'm not sure what you want to decay.
So this Rij of the previous slide.
Yes.
If you order the energy, is there a notion that they decay in some way?
Oh, you mean as you go on? That's encoded in the f function. So the f function is supposed to pull out all that secular behavior, and the r's are defined the way I've defined them to always have all the way out unit variance. But the f function will definitely fall off. And in fact, there's a bound on it has to fall off at least exponentially in omega with a constant that's set by the temperature.
So if there are degeneracies in the spectrum, are we supposed to just choose one symmetry sector and apply this, or?
I didn't mention this. I'm assuming there are no degeneracies in the spectrum, which will be generically true in the sorts of systems that are going to obey this anyway. If there are, there have to be not very many of them. Well, let me step back. It depends on what's causing the degeneracies. If they're caused by some symmetry, then we should work in some particular sector of the symmetry. If they're just accidental, I'm assuming there are a few of them, and so then there would be some surviving phases here, but hopefully they will be a small contribution to the total. What am I doing? All right, so when does it hold? It's expected to hold for not two weakly coupled systems with no or few conserved quantities and no or weak disorder. Again, so just starting at the bottom, if localization, many-body localization occurs, that will not reproduce the ETH matrix element structure. So we have to have either no disorder or disorder that's weak enough not to cause localization. If there are other conserved quantities, we have to take them into account either by, as I just said, for discrete symmetries looking in a particular sector, or by constructing a generalized Gibbs ensemble where we think of, we think of everything as a function not only of the energy, but also the other conserved quantities. So we would then need to add variables to the ETH matrix element formula that correspond to each conserved quantity. And then those would be equivalent, the diagonal terms would give, final positions here that agree with the thermal ensemble, oops, I'm going backwards too fast here, that agree with this, but now computed in that generalized Gibbs ensemble. Okay, and this is if you have a few conserved quantities, like maybe angular momentum, if you have put your system in a spherical box or something like that. But if you have an infinite number, as in something like the XXZ model, then that's a qualitatively different situation, and basically the ETH matrix element formula does not hold. Okay, so this is the generic claim. Such systems are often said to be chaotic. We could ask just how weakly coupled can they be, and a number of people have investigated this in different specific systems. I think there's no general answer to that. To give you some intuition for this, I want to say a little bit about the way I first thought about this. Let's think of a dilute gas of hard spheres in some box. And this is basically a very fancy billiard system in which the simple billiard is we think of a particle bouncing around inside some shape, here just in 2 dimensions. But the hard sphere gas, we can think of, we can think of the point that gives us the coordinates of all the particles. We can think of that as a 3n dimensional billiard in which that point is moving around. And we can distinguish integral motion from chaotic motion. The red line here is a single trajectory, classical trajectory. And in the square, it bounces around in a regular looking pattern. And in the Sinai billiard, as it's called, a circle inside a square, it bounces around in a chaotic manner. So such systems were the subject of interest among a group of physicists in the 70s and 80s. And Michael Berry, who did a lot of work on the mathematics of quantum chaos theory, the quantum mechanics of a system that's classically chaotic, he had a conjecture that if you were to write down an energy eigenfunction for one of these systems at a sufficiently high energy, so it's there are multiple wavelengths in between any 2 walls, you could of course describe that as a superposition of plane waves, because inside the box there's no potential, so a free particle plane wave solves the Schrodinger equation, the time-independent Schrodinger equation. And then, but this K, it will now have a magnitude that's fixed by the energy, but its direction can vary. And then you can superpose Ks of same magnitude but different direction with some coefficients, and Berry conjectured that these coefficients would look like Gaussian random numbers. Okay. At that time, there weren't computers that could do this, but this turns out to be true to a remarkably good extent. So here are some nice plots by Arne Baker. On the right is an actual energy eigenfunction in the cardioid billiard, which is this cardioid shape and produces chaotic motion. And on the left are just Gaussian random waves, which were superposed with random numbers pulled out of a random number generator. And you're supposed to look at these and think, yes, those look alike. And of course, we could do fancy statistical tests and so on, and it still holds true. Okay. And then the punchline for ETH is that if you take your local observable, which in this case means I'm going to look at the kinetic energy of one particle, the ETH ansatz for the matrix elements that I wrote down earlier follows from these very random wave functions, which I'm not going to explain why that's true, but it's true. Okay. Some very important numerical work was done sometime later by Marcos and collaborators on a system of hardcore bosons on a lattice. So this is a system that doesn't have any sort of nice classical limit. The purely theoretical analytic work that can be done is mostly based on taking a classically chaotic system and quantizing it and trying to analyze that. We don't have that here, but such systems are much easier to study numerically, and so what they did was consider this system of hardcore bosons on two different kinds of lattices. One, just a simple line lattice, and the blue dots are occupied at the start and the white dots are unoccupied. Or this broken square lattice where the particles all start on this side but then have one gateway into the rest. Okay. And so n here is not very large. The occupation number is 8, I think. So, but nevertheless, they did computations on this, and so what they are plotting here is the expectation value of a Fourier mode of the number density. So the x-axis here is indexing the Fourier mode, but what each of these is just a different observable, or a different linear combination of local observables. And there are actually 4 curves being drawn here. The expectation value computed in 2 different particular eigenstates, the microcanonical expectation value across some slice, and the diagonal expectation value where you weight by the c-squareds that you got from the initial state. And ETH says those should all be the same, and they're all the same. So that's the, okay. That is, of course, for the, quote, chaotic, unquote, lattice on the top. On the bottom, there are a bunch of conserved quantities, and this doesn't hold. These different averages don't agree, and we get different answers. And to fix that, as they said, we would need to go on to a generalized Gibbs ensemble that took into account all the different conserved quantities. All right. So, some more recent developments. Again, here's the formula. It's useful to write down a thermal density matrix just as a theoretical tool, not as a proposed state of the system. And the inverse temperature beta will be fixed by saying that the expectation value of the energy is E, which is going to be the E that appears up here. And then it immediately follows, basically from everything I've already said, that this A of E function is then just the thermal average of A at the inverse temperature that gives the correct energy. But we can do fancier things. If we look at the observable in the Heisenberg picture and compute this time correlation function, so I have an A at time 0 and an A at time t, and then a slightly funky thermal average where instead of just putting a single row here, I split row in 2 and put a square root here and a square root here, and I term. This will be, after some manipulations, just the Fourier transform of the square of the f function. So this relates the f function to this correlation function. And so if you have some characteristic time scale on which you think this should decay according to whatever your system is, that time scale is embedded in this f function. And typically such time scales will be of order 1, not of order n. And that's why I said we should think of omega as order 1, because otherwise we'll mess up the Fourier transform. All right, we can do even more. We can generalize that to a multi-time correlation function. And this splitting of rho, this has appeared in the literature in various guises. There's a very nice paper by Laura Follini and Jorge Kirchen from a few years ago, in which they pointed out that if you want to get non-trivial higher point correlation functions, in particular the out-of-time order 4-point function that was a subject of much talk a few years ago, the statistical average of these matrix elements, this overbar means statistical average in energy ranges for each index. If these were purely Gaussian, you would just get these Kronecker deltas. But they pointed out that you need corrections to that in order to get non-trivial higher point functions. And that these corrections should be very small on the scale of the matrix element, but these turn out to be just as important basically because a Kronecker delta removes one sum over states. So that's removing one e to the plus s, and then we have an e to the minus s. 1 minute. Okay. Happily, this is my last slide. Recently, Sylvia and Laura and Jorge and also Daniel DeFerris and these folks have been writing down in different formalisms a random matrix model for A that incorporates all of these higher point, in principle, all these higher point correlation functions. And for simplicity, I'm going to assume I have an A goes to minus A symmetry, like for a spin, for example, and so I only have even functions here. So just this would be, and without a K, this would be a standard Gaussian random matrix model. This K function, we can modulate how this is the width of the Gaussian with the energies. And if we didn't have any of these other terms, this K function would basically be the inverse of the F squared function. But these groups in different languages said we should put in these higher point functions, and by adjusting them appropriately, we can reproduce whatever the higher point correlation functions are. But then we can think of an individual matrix element as being drawn from this more complicated distribution. And for those of you who know something about large N quantum field theory, these are then given, the correlation functions are given as sums of planar diagrams. So this is a relatively new idea, and I think it's very interesting, and I would like to understand it better. It may be a key to making further progress in this and to dialing ETH into a specific system and going back and forth between the two formalisms, the correlation functions and the probability distribution. There may be some interesting physics lurking in there. Okay, so I've told you what eigenstate thermalization is, I told you what follows from it, I told you when it holds, and I told you about some recent developments. So, thank you.
Thanks a lot, Mark. Okay, so questions.
Thank you for a very good overview. Can you comment on the relation between the things that are not kind of captured by the ansatz itself and like simpler observables, not autox, but maybe transport like diffusion or some simpler things that characterize how you approach the equilibrium and not just the equilibrium itself?
No, well, that's a really good question, and I don't know the answer. That's one thing that I find intriguing about this formalism is it seems like I could choose all these coefficients and reproduce any set of time correlation functions that you might give me, but there's still information in this that and in particular, this agrees with and reproduces that these correlations have these exponentially small corrections. But you can write down systems in which these are not Gaussian at all. If you look at matrix element distributions in XXZ, which Marcos and other people have done, they're not Gaussian. They're closer to log normal. They're not log normal either, but they're closer, much closer. All right, this says no, you're not going to get log normal out of this. So there's something else, right? So this is more information than just the correlation function. But, if I give you a set of correlation functions, is the system that reproduces those necessarily ETH, or is it necessarily something else? The big question, I think, what is the connection between matrix element structure at this exponentially small microscale and correlation functions at a larger scale? Very general.
Thank you for the very interesting talk. I was just wondering, when you talked about the unequal time correlators, would these systems obey principles like fluctuation dissipation? if you calculated those from the unequal time correlations?
Yeah, there was this now very well-known paper by Maldacena, Schenker, and Stanford called Abound on Chaos, in which they said that if you have an out-of-time order correlation function in a system with a small parameter that allows there to be a period where this correlation function grows exponentially, that the rate of that growth is bounded. Okay. And they called that Abound on Chaos, but it seems to be a very general bound. So a number of people, Sylvia and others, have shown this bound from general principles. And I have a paper with my former student, Tatana Murthy. We said we derived it from ETH, but we were really lying because it really just depended on the correlation function structure and not on the matrix element structure, which didn't really understand at the time. But anyway, so I think that bound is a very general bound. That I think you would agree with that, yes. That doesn't really have anything to do with chaos. It's just some uncertainty principle-like bound.
Thank you.
Can you define what makes OTOC non-trivial here in this context? You were saying non-trivial OTOC property.
Oh, well, if you wrote down, write down this with n equals 4 and your times in out-of-time order, and then plug in the ETH matrix element formula, and then say, oops, and then say, oh, what am I doing? Where did it go? There it is. ETH matrix element formula, and then say, okay, I'm now going to replace the product of the 4 R's by this statistical average, and you don't put in these terms, your 4-point function will end up being a product of, or a sum of products of 2-point functions. It's basically Wick's theorem. Okay. But that's not enough to find this non-trivial behavior. Okay, so the non-trivial behavior comes out of this term.
You mean like exponential decay and...
Yeah, anything that's not, that you don't get from squaring a 2-point function.
I wanted to make sure I understood Barry's conjecture. Do you mind going back to that? So, right. So you're saying that his conjecture was that if the wave function has this form with Gaussian random, you get an integrable, but if it's not that form, you get a chaotic system of the right type.
No.
Okay.
So this form applies to any billiard because it's just saying inside the billiard, a plane wave is a solution.
Mm-hmm.
And then for any particular billiard and any particular energy, we then have to compute what these chi's are, and we want to choose chi's so that whichever billiard we have, the wave function vanishes on the boundary. That's the boundary condition. Okay. Barry's conjecture is that for a chaotic billiard, but not for an integrable billiard, these chi's will look like Gaussian random numbering.
Okay.
In an integrable billiard, they have a lot more structure.
Okay. And the next slide on the cardioid, so would you expect for, let's say, a boundary that was a Euclidean tiling or do you expect features that deviate from?
Yes, you would see. Well, if we said this box, so this box is not a billiard. This is just the region in which he's showing a sum of random waves. If we said this was actually a billiard, then we would the eigenfunctions would just be sines times sine, sine kx, sine ky, and we would see we would see a corrugated box structure for any eigenfunction. So we see some very clear structure. It wouldn't have this random appearance.
Okay. And the choice of the cardioid was just?
It's a chaotic billiard, which may or may not be easier to do the numerics on. I don't know.
I see. Okay. Thank you.
Hi. Could you talk more about examining the property, like the importance of the local observables in this? Because a lot of times in conventional statistical mechanics, we're interested in, pressure and volume, like bulk properties of the system that are not local.
Well, volume is the way this works, unless you have some wall that's moving, volume is a fixed thing. Pressure, I would get by measuring, I would ask for the kinetic energy of a particle near the wall, right? So I think I can convert all those things to local variables. But more generically, you could ask, how many degrees of freedom am I allowed to put into one of these local observables before it doesn't work anymore? And there's a nice paper by Jim Garrison and Tarun Grover from a few years ago that says you can go almost all the way to half the degrees of freedom, and it will still work.
Hi. I don't know if I missed a comment of yours, but since this is a long-range conference, I'm asking, what about long-range interactions?
Well, in this context, I don't think they do anything specific one way or the other. I think I could construct a long-range system that's anywhere on this spectrum of systems from fully integrable to fully chaotic. So it's orthogonal to this conference in some sense. Sorry.
What happens to the ETH in vicinity of finite temperature phase transition? Let's say in 2 dimensions, if it's a first order phase transition.
Well, the short answer is I don't know. I think to the extent that I'm going to stop there. I don't know. It would be interesting to see if anything special happens. My immediate reaction is the formula will still work, but the functions may change sharply at that energy. I think that is the answer, right? So you can have, if it's a first order transition, the A and the F functions can take sharp jumps at the transition point, and second order they would be continuous, but discontinuous first derivatives. I think that's what happened.
Thank you. Can you comment on what can we learn when the ETH fails, for example, for some local observables or for some initial states?
Well, if we expect it to hold and it fails, that's an interesting phenomenon that we would then like to find out why. And usually why means there's some conserved or almost conserved quantity that maybe you didn't know about. So this is not historically true, but one could have discovered that the XXZ model was special by computing these matrix elements and finding out they're not Gaussian, they're completely different. So in a history where people did numerics before beta figured out the beta ansatz, we might have discovered that that system was special in that way.
Yeah, just to follow up on the question on long-range interactions. If the long-range interactions are very long, like, for example, a power law where the exponent is smaller than the dimension, do you need to worry about this breakdown of ensemble equivalence? So basically, ETH should probably fail for that region?
If ensemble equivalence is breaking down, then definitely you have to rethink what ETH is.
So let me make a comment on that. The structure, when there are power law decaying interaction of the spectrum, changes a lot. So the dynamics is very slow because there is some sort of scarred structure similar to what we're going to hear later. So some things have been done in that direction, but it's quite different from what we hear. Okay, I think we can thank Mark again.